Good morning, Honors Math 1. Good morning to you. I'm glad you're here. Thanks for dropping in on this first class of a new semester. Let's start. If you recall, way back in chapter 3, we did an activity kind of called the Great Race, and we were modeling racers on tricycles. And if the equation of one of the racers was y equals 3x plus 4, we know that if x is recording the time in seconds, and if y is recording the distance from the starting line in feet, we know that for this particular person, when x is 0, that means the race is starting, yet they're magically 4 feet from the start of a race. So this equation shows me two things. It shows me that they have a 4-foot head start, and it also shows me that every single time 1 second goes by, their distance from the start increases by 3 feet. So their speed is 3 feet per second. This form of an equation is nice for making such observations. We call it the slope-intercept form. And when we look at it, we can see both where the racer begins, like where we begin on our y-axis, right? When x is 0, y is 4, and it can tell us our rate of change or how fast something is changing as x changes. It is possible that we will not always have such a nice equation. In fact, our equation could be written in a different form. One of the forms that our equation could be written in is something that we called standard form. In standard form, generally, my perception of it is that all of our coefficients are integers. So we don't have fractions and we don't have decimals. And it's easy, if you have an equation that's not that in that state, to multiply both sides by something to get rid of fractions or decimals. But the other thing is that all of the x term typically is first, so I'm going to write minus 6x and then plus, and then our y term, and then on the other side we write down the constant equals 10. So we would call this the standard form. Now in this form, it's not so easy to see the slope, and it's not so easy to see the y-intercept. Now we could make a table of values for this situation. We could pick x's and find the y's that make this true. But the other thing that we could do is we could rewrite it so that it is in standard form. In other words, we want to change this so that y is completely by itself. And if I wanted to change this into standard form, that was loud, I would do that by adding 6x to each side. So if I added 6x to each side, on the left hand side this would become 2y, and on the right hand side it would be 6x plus 10. And if I divided both sides by 2 now, I would see that y equals 3x plus 5. So now I can see that for this equation, right, I have a y-intercept at 5. And for this equation, I can see my slope is equal to 3. Not immediately visible here, right, but definitely visible below. My slope I've double underlined, and my y-intercept I've single underlined. So again, this form is called standard form, and a, b, and c should all be integers. So ax plus by equals c. Now, if I have an equation that's presented in standard form, I can change that to slope-intercept form. We just demonstrated how to do that with this example above. Another form of an equation that is useful, and it really speeds up work, especially I notice this from pre-calc and calc students, is something that we're going to call the point slope form. And the point slope form of a linear equation looks like this: y minus k equals m times x minus h. Looks a little confusing. The way that I work with it, I don't think it's, I hope that you find that this isn't too taxing. There are two things here. M, fortunately, is not a lowercase m. M is what we expect it to be. It's the slope. But the other thing that we have is we have this point. This point located at h comma k, an x and a y. And this is some point that we know. So for example, if we consider we had a slope of 3 above. Let's consider a line that has a slope of 3 and goes through 211. So we're going to say m, our slope is 3, and it goes through the point 2 comma 11. So if I know that information, I know what the slope is, and I know a point that lives on the line, I can write down the equation of that line in one step in point slope form. And here's how I say it. It's always going to be the y minus the y value that I know, right? If you look closely, k is the y value that I know for my point. So when I see this, I say y minus the y value that I know equals the slope, 3, times the quantity of x minus the x value that I know. And the x value that I know from my point is 2. So if I look at this, I can transform this equation also, if I wanted to, in slope-intercept form. And I would do that by rewriting the right-hand side using the distributive property. So this is going to become 3x minus 6. And then if I add 11 to both sides, I get y equals 3x and then plus the number 5. So I can see the exact same thing happen here that happened above, right? I end up getting the exact same equation. In both cases, it's y equals 3x plus 5, y equals 3x plus 5. So these are two equivalent equations. Now it's going to take a while before you feel comfortable with this, and I want you to think about the strategy that you use so that this becomes not an alarming thing to look at. It's not so confusing. One of the things that I think helps me is just reminding myself to say it, to say what this is a certain way. Y minus the y value that I know equals the slope times the quantity of x minus the x value that I know. So if we're given the equation 0 equals 3x plus 5, I could ask, how many solutions does that have? Well, I would take away what? I would take away 5 from both sides. So I would get that negative 5 is 3x. And then if I divide both sides by 3, I get negative 5 thirds is x. So I can see that my solution is the single value 5 thirds, negative 5 thirds. But if I was to consider the equation y equals 3x plus 5 and ask, well, how many solutions does that have? Well, that's a little bit more complicated, right? That ends up having lots of solutions. In fact, for y equals 3x minus 5, I did put plus 5 below. Actually, let's change that. Let's look at 0 equals 3x minus 5. Actually, I think this is lifted from the book. 5 equals 3x, and for this equation, positive 5/3 is what x is. So this equation, right, this equation, 0 equals 3x minus 5, has a single solution, 5/3. But the equation y equals 3x minus 5 has lots of solutions. In fact, any point that lives on the line is a solution. And it's not just the lattice points, right? It could be any point in between. But when I look at this, I'm looking at a whole collection of xy points that make this equation true. Tons of them. Let's take a look at a different equation. So let's look at the function y equals 0.2 x to the third times x to the third minus 5. And I've graphed that here. So we can consider this graph. And if I ask the question, well, how many solutions does this equation have? The answer is it's uncountable, right? Any xy pair that lives on the line is a solution, right? There are lots and lots and lots of xy pairs that are solutions. In fact, it appears that when x is what, negative 3, 1, 2, 3, it looks like when at negative 3 y is negative 10, it looks like this thing with integers is a solution. I say looks, I'm not sure that it is. But again, the question is, how many solutions does it have? It's got a lot of solutions. All those are solutions. If I look at this graph and I say, hey, does it appear that 5, 8 is a solution? I would have to say, I don't know, Mr. Roberts, because 5, it runs off the graph and I can't see that. But I could graph it again. Let's see, math. Let me graph in 2D. And I'm going to change it a little bit. I still need to want to be able to see 10. But let me insert this one on the page. So here's a new version of that same graph. And on this version, it looks like this is 1, 2, 3, 4, 5. So these are each 2. 1, 2, 3, 4, 5, 6. So this is where x is 5. And it's asking, does 5, 8 look like its solution? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, if you ask me, does it look like a solution? 5, 8 definitely appears to be a solution. Explain how you could use the graph to estimate the solution to this equation. So let's say that I had this equation. I ask you to tell me, hey, I want you to solve the equation y equals 0.2 x to the third minus the number 5. Well, if I look at this, right, this is the definition of this curve, right? This curve was y equals exactly 0.2 x cubed minus 5. So I want to know what value of x is going to make this function go through and become the number 2. Right here. Not 4, but 2. Right here, this line. So I can see this line that I've drawn is the line y is equal to, oh no, I want to know when it's 4. Third time's a charm. 4. I want to know when y is equal to the number 4. This is 2, this is 4, 6, this was 8 and 10. So if I'm asking, what's the value of x that makes it look like 4? Well, somewhere in here, there's such a number, right? You can see the number is 1, 2, 3, a little bit bigger than 3, but less than 4. So somewhere in between 3 and 4, there is a number that's going to make this function become equal to 4 right here. So if I was to think about that point, I could say, well, that point, I'm being asked to find when it is 4, so when y is 4. And to me, I don't know, these are each by 2, so that's 1, 2, 3, 4. 1, 2, 3, 4. So it looks like it's bigger than 1, 2, 3, 4, bigger than 3, so maybe like 3.8ish, somewhere in there. So graphically, I can see that when x is about 3.8, this function is going to be close to the number 4. And actually, out of curiosity, I did pause this and check, and you probably noticed this too. 3.8 is too big. I think that made it close to 6. So I think probably it's more like 3.5 or 3.56 is probably closer to the value of x. But definitely we have a strategy for figuring out the answer to this equation based on using this graph. And we're going to finish today by looking at question 5, so if you want you can follow along in the book. But one of the things that we've been practicing is rewriting equations in different forms. So one equation, work equals force applied times the distance that you have to move something through, is a relationship between the force and the work applied over a certain distance. You could take this equation if you wanted to know, for example, in the book it says, what is the force needed to move the piano given the amount of work applied and the distance moved? What is the force needed? So if I was asked for what is the force, right, Yoda would say, divide both sides by d, you must. So if I took and divided both sides of this equation by d, I would get the force is work divided by distance. So again, all that we're thinking about here is if we're given a relationship between, 2, 3, or more variables, and we want to isolate or get one of the variables alone, we're still just using here the division property of equality. I'm dividing both sides by d to get f alone. Another equation is that temperature Fahrenheit is equal to roughly 9 times the Celsius temperature divided by 5 plus 32. So if the question was, what is the temperature Celsius, when you know what Fahrenheit is, this is not the best equation to work with. So what you could do is subtract 32 from both sides. So force minus 32 equals 9c divided by 5. And to continue, I would multiply both sides by 5. So this whole thing has to become a quantity, force minus 32. And I'm going to multiply it all by 5. So that's showing both of those terms would be multiplied by 5. And over on this side, it's 9c. And then I'm just going to divide both sides entirely by 9. So I could say 5 times force, or Fahrenheit degrees, minus 32, all divided by 9. This works. And there's certainly more that you could do with this as well. You don't have to leave it in here, but roughly you're subtracting 32 from your Fahrenheit, multiplying by 5, and then dividing that result by 9. There's one more in here. It says the symbol rho, and this is it, it's a Greek letter rho, equals its mass and volume. So mass divided by volume. And rho is the Greek letter that we use to denote something called density. It's a property of anything has a density. Styrofoam has a very low density, gold has a very high density. And somewhere in there, if you're less than the density of water, your object can float. If you're more, you would sink. So sometimes science use, oh, they're just explaining that, yeah, we do use not just letters, but we'll use Greek letters like rho. Also in math, we use Greek letter pi for the ratio of a circumference to a diameter. But this question says, what is the mass, m, of a precious stone given its density and volume? So this is like, tell me what, solve for mass. And to get mass alone here, you're just going to take the density, rho, and multiply both sides by v. And then you have this now mass. So you know that the mass is equal to the density times the volume. So again, given an equation, if you need to get one of the variables alone, we should be able to rewrite it so that that reality becomes the reality. Today your homework is to do questions 7 through 12, questions 7 through 12 in chapter 6. So chapter 6, questions 7 through 12. I will be passing out assignment sheets next week, but for now, you're just going to have to keep track of these. In general, we will be doing one section a day, and I think there's no problems that I'm planning on skipping. But again, just keep checking in with me, 7 through 12. Well, I'm glad you're here, and I know after a long winter's break of not necessarily getting up and doing things, it's time to think about those routines that we put ourselves in so that we're likely to accomplish the things we want to accomplish. So that you're here, you're listening, and you're doing these problems and listening to this talk is a good indication that you're on your way. So I hope to see you online today. I'll be taking calls all day long. I'll have an open session. It is not mandatory. If it is mandatory, I'll definitely say that it is. But today, it's just going to be an open drop-in, and I look forward to seeing you again soon.